Today I've got a really cool problem to do with football. This is all about the number of possible ways you can end up with players on a football pitch. Obviously, I've modified the numbers to fit with this problem, and you can easily tweak it to represent other sports and things like that. But it's got a really, really elegant solution. So I'm going to show you the kind of brute force method first, and then show you why there's a really, really elegant solution. Okay, let's have a look at the problem. A football team consists of one goalkeeper, so it's supposed to be a comma, four defenders, four midfielders, and two forwards. So one goalie here, four defenders, four midfielders, and two forwards. There are four possible substitutions that can be made during the game. There are four substitutes on the bench, so one from each position. So we got on the bench, which maybe here, we've got a goalie, we've got a defender, we've got a midfielder, and we've got a forward, and they're ready to come on at any point during the game. Um, Now we're told that at the end of the, oh sorry, I forgot to read this bit. A substitute can only replace a player from the same position. So if you're a midfielder on the bench, you can only come on for one of these four players. Similarly, if you're forward, you can only come on for one of these two. There are only 11 players on the pitch at the end of the game. How many players, how many possible sets of 11 players could finish the game? So, for example, if the team decides to have no substitutions during the game, it would just be the same as the starting 11. But if, let's say, they decide to swap the goalies at some point, then that would be another possible set of 11 players. The question is, what is the total number of sets of players that could finish the game? Do give this problem a go. It's got quite a nice solution. The way I'm going to be showing you this, firstly, the brute force way, is just to kind of consider the four possible scenarios, or maybe five if you think about it this way. So the five being how many substitutions they use, so the number of subs. So if I make like a little table here, and then this will be like the number of sets of final 11. It's supposed to be 1L. Okay, so if the team decide to make zero subs during the game, well, that's pretty obviously then going to give us only one set of the possible final 11. It'll be the same as the 11 that started off. Okay, if the manager decides to only make one sub during this game, well, there are 11 players initially that start on the pitch, and the manager can choose any one of those 11 players. Let's say that they choose this guy, and then that guy gets subbed off, and that's it. In which case, there's 11 possible finishes and 11 possible sets of final players based upon the choice of that original player that they sub off. Now, here's where things get interesting. What if we make two subs during the game? Well, in fact, maybe I'll give myself a bit more space here. The idea is, well, we know that those two subs can't come from the same position. So if one of them is a midfielder, the next sub can't be a midfielder. It has to be a defender, goalie, or forward. Okay, so let's think about it this. If it was a forward and a midfielder, so at some point in the game, one of the forwards gets swapped, and at some point in the game, one of the midfielders gets swapped. How many possible ways are there to do that? Well, I could swap this forward out, and in which case I still have four possible choices for which midfielder I swap out. Similarly, if I decided instead to swap this guy out, there would still be four possible choices for which midfielder I choose to sub out. So that gives me 2 times 4, in other words, 8 possible choices. So I'm going to write that as 2 times 4. Now that gives me, if the two people I choose to sub are, one's a midfielder, one's a forward. What if instead one's a forward and the other is a defender? Well, we get the exact same logic. We get another 2 times 4, like so. Similarly, if I do this, if I decide to sub one forward and one goalie, that's going to give me 2 times 1 ways of doing that. And I'm just going to kind of consider all the possible pairings. So what if I have midfielders and defenders? That's going to be 4 times 4, so 16, like so. What if I do midfielders and goalies? That's going to be 4 times 1. And the last possible pairing is if I choose one of my subs to be a defender and one of my subs to be a goalie. So it gives me another 4 times 1. And now I just need to add these up. So I've got 8 plus 8 is 16, plus 2 is 18, plus 16 is 34, plus this 8 here gives me 42, like so. Okay, so that's if I make 2 subs during the game. Okay, great. What if I decide to make 3 subs during the game? Again, this is something we've got to be kind of careful of. So let's say we choose these positions here. So we choose one forward to sub, one midfielder, one defender. Well, oops, sorry. So this midfielder, we have two possible choices for which guy we choose to, this forward, we have two possible choices for which forward to sub off. And then for each of those, we have four possible midfielders we can sub off and four possible defenders. So we get 2 times 4 times 4, like so. Now, what if instead I decide to sub a forward, a midfielder, and a goalie? Well, that's going to give me 2 times 4 times 1. And similarly, you can kind of see where this is going. The other possible combination would be if I do a forward, a defender, and a goalie, or if I do a midfielder, a defender, and a goalie, like so. And now we can just add this up. So this is what 16 times 2, so 32 plus 8, that's 40. 48 plus 16 is 64, like so. Great. And last but not least, what if we decide to use all four of our substitutions? How many possible ways are there to do that? Well, this is actually kind of an easy calculation. You have to choose one of the forwards, one of the midfielders, one of the defenders, and one of the goalies. So it's simply going to be 2 times 4 times 4 times 1. And if we work that out, that's 16 plus 2, so 16 times 2, which is 32, like so. And now I've considered all the possible cases and the number of sets of final 11 players that I'd be left with. I just need to add up these numbers. So 1 plus 11 plus 42 plus 64 plus 32. And you can check if you add those up, you get 150. So 32 plus 64 gives you 96. Plus the 42 there gives you 138. Plus the 12 here gives you 150. It's a very weird looking 50. Okay, cool. So that's the kind of nuts and bolts kind of brute force method, I guess, if you like, of getting to an answer. And it does the job. Here, the numbers are small enough for us to kind of compute this. What's the elegant way to doing this? Well, the elegant way is actually, if we observe what we did in the brute force method way, we had this calculation here. If we look at this calculation we did here, this looks quite nice. What were we doing? We were kind of adding up the product of, so if I write down the numbers 1, 2, 2, 4, we were kind of using, sorry, 1, 2, 4, 4, sorry, like so. What we were doing is we were just picking pairs of these numbers and multiplying them together and considering all 4 choose 2 pairs we could have chosen. So 4 choose 2 is 6, which is why we have 6 terms here in this calculation. And we were considering each of those 6 pairs and the products. So I sometimes refer to that as the sum of the byproducts. So this, I'm just going to, for the time being, denote as the sum of alpha beta. And maybe you can guess where this is going. Similarly, when we had 3 subs, we were considering the products of triples of these numbers. So 2 times 4 times 4, 2 times 4 times 1, 2 times 4 times 1, and 4 times 4 times 1, which I'm going to write as the sum of alpha, beta, gamma. And this thing here was just the product of all the numbers here. So this was just alpha, beta, gamma, delta. Again, if this notation doesn't mean anything to you, ignore it. Don't worry about it. And this thing here, this 11 was just the sum of these numbers. So 4 plus 4 plus 2 plus 1. So that was like the sum of alpha, like so. Now, why is this interesting? Well, if you've seen Vieta's formulae before, you'll know that if I take this polynomial, x plus 1, x plus 2, x plus 3, x plus 4, so no, x plus 4, x plus 4, if I was to expand this out, I'm going to get an x to the 4 term, and then I'm going to get a plus the sum of these numbers. So if I call this number here, so these numbers I'm going to call like alpha 1, alpha 2, or yeah, so alpha 1 is 1, alpha 2 is 2, alpha 3 is 4, alpha 4 is 4. So it's going to be x to the 4 plus alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 x cubed, and then plus, like, I'm going to kind of shorthand it, alpha I, alpha j. So it's kind of like this alpha beta term I've written here. So the sum of all the possible distinct pairs of I and j. So I, let's just say, is less than j here, of x squared, sorry, and kind of so on. So then it would be the sum of the tri-products. So the sum of alpha I, alpha j, alpha k, x cubed. Again, only considering one of those, like, so I'm not including permutations here, x. And then lastly, alpha 1, alpha 2, alpha 3, alpha 4, like so. So if I was to expand this out, I get this polynomial here. And what we noticed from doing, oh gosh, I'm not sure why the screen keeps moving. Sorry. What we noticed from doing the brute force method is all we had to do is add up these four numbers, which corresponds in this quartic here, adding up the four or the five coefficients, because we think of this coefficient as the one being this one up here. Now, how can we add up the coefficients of a quartic efficiently? Well, the trick is to just substitute in x equals 1. Because if you substitute in x equals 1 here, um, this term here just, well, you can kind of ignore the x. Same with this here, same with this here, same with that there. And now you're just adding up those numbers. But the beautiful part about this is we already have the factorized version in which we can substitute x is 1. And if I do that, I get 2 times 3 times 5 times 5. And if we work that out, that gives us 150. So the same as this number here. And so that's a shortcut trick, I guess, if you like, to solving this. I guess obviously this trick is only nice if you like have seen this type of problem before. But now I encourage you to try and do this with different sized teams, with maybe different numbers of positions and different numbers of substitutes and all that sort of stuff. And see if you can find kind of like a nice general result. But it's really cool how this quartic has some relationship with choosing the number of possible like football team arrangements that you could have. Anyway, this is a really, really cool problem. This is actually based off of a senior maths challenge problem I saw recently, but I've tweaked it slightly just to make it a little bit more interesting and to use this result. Anyway, thanks so much for watching. I'll catch you in the next one. Have a great day.